Good morning, everyone. I'm happy to have Dr. Chang Liu as our speaker today. Dr. Chang currently is a postdoc researcher at UC Berkeley, and he got a PhD from University of Maryland, and his research interest focus on intersection of deep learning, security, and the program language. He won several best paper awards. Thanks.
Yeah, thank you very much for Danny's introduction. So today I'm very happy to be invited here to share my experience on how to use deep learning to help enhance the security and programming language. And okay, so let's just start it. Okay, so consider we are just a average PhD student. Okay, so I shouldn't use the term average, but so what I mean is that assume that we are not having any security background, then we are asked to develop some system, for example, like the autonomous driving system or the cryptocurrency contracts, or even the recommendation system. So then how can you do to guarantee the security of this system? So first of all, why do we want to guarantee the security of this system? Because otherwise, if you don't make sure they are secure, then you will be on the headline of some news, right? For example, your information will be leaked to publicly and accidentally, and also maybe in the most terrible case, then the car that you are driving will crash into some other cars, and also you may happen to lose a lot of money, right? So in all these different applications, it highlights the importance of making sure that the systems that you are building is secure. And actually, this is a challenging problem. So my research focus is how can we use deep learning technologies and also the program analysis technology to guarantee the security of when we build this kind of system. So my main research focus is on these programs. And then in today's talk, I will talk about two aspects. First of all, I will consider, so if we represent these programs as an end-to-end neural network, then what will be the problem? And then I will reveal that this existence of these adversary examples will hinder the application of such systems. I will very soon introduce what I mean. And later, and for the second part of the talk, I will introduce our work using deep learning to improve the security of different kinds of programs. Okay, so let's just get started. So in recent years, there are more and more interest to kind of represent the entire program as an end-to-end neural network. For example, this is a multi-layer perceptual network that can classify the input image, which is just an image, into its class. So this task is called image classification. And it has achieved a huge amount of success in recent years. And actually, some latest architecture has been able to surpass humans' capability in this task. However, the existence of so-called adversarial example will hinder such applications. For example, this is a ResNet model. So on the left-hand side, on these three columns on the left-hand side, they are just original images in the dataset. So, and then for a well-trained model, they can classify all of them correctly. Oh, sorry, I don't know what's wrong with this. But it happens sometime, but I don't know what's wrong with that. But right, so but we can add some perturbation that is in the middle row, and then we got a result image which look identical to the first column to human beings, but for the neural networks, all these images will be classified as an ostrich. Right, so these examples are so-called adversary examples, and we all know that they are not correct. And more importantly, this will severely hinder the application of some security-sensitive application. One of them is this autonomous driving system. For example, this kind of system will rely heavily on different sensors to sense, for example, the traffic sign along the road. And for these two signs, I think for here, so anyone can tell the difference between the two, right? Okay. Right, you want to have a try? Right. I'm very sorry about this problem, but I don't know why. It just slides automatically. But actually, on the paper that presented in paper, that the top image is shown as a stop sign, but the bottom image is reported as a yield sign. So and then so the difference between stop sign and yield sign may be fine, but for sometimes if you predict a stop sign as for example as the speed limit sign, then that will be a big problem because you won't stop there, right? So in all these different respects, it is very important to study these adversary examples. Okay, so we considered the existing work, and then we found that most of them are only considering this image classification problem. And then also they all consider the target model is null. That means not only the parameters in the model are null, but also how the network used those parameters to compute the final result is null. So in our investigation, we want to see two aspects. The first one is whether we can weaken the threat model. For example, whether we can generate these adversary examples when the target model is not null. Also, we want to see whether other classes of models are also vulnerable to these adversary examples. So here is a real system that is called clarify.com. This is a startup in Bay Area. And then the main service that it provides is that user can upload the image into the system, and then the system will return a couple of labels that they believe this image contains. And then for this system, so we are not collaborating with their company, but we just use their system to see whether we can attack that. So for this system, the model that they use to make the prediction is a null. Also, their training data is a null. And more importantly, even though this label set is a null, because we don't know what label could be returned from the system. So and then we want to see whether we can attack that. Okay, so right now I want to briefly explain how these adversary examples are generated. So the basic technique to generate this adversary example is through this maximization problem. And then, so we assume the model is f theta x, where theta is the parameter in the model, and L is the loss function, just as the same one as we use during the training. So during the training, we want to minimize the loss, where the parameter to optimize is theta. But here, for adversary example, we want to maximize the loss. That means we want the prediction to be far away from the ground truth. So and then also we don't change anything about the parameter, but we only change the input, so that we want to find the input x star, which can make the prediction far away from the ground truth. And then also we don't want to generate an arbitrary input. We hope the input, these so-called adversary examples, are still very close to the original input. So that is why we have another constraint here. We hope, so d here is a distance function, which is a metric. And then we hope the distance between two instances are very close, for example, bounded by a constant b, right? So by solving this, so all different kinds of adversarial all different kinds of algorithms to generate adversary examples are solving this problem or approximating the solution of this problem. So I will enumerate two classes. One is called the iterative approach. That, for example, we can use a gradient descent-based algorithm. For example, in most of our approach, we use the Adam optimizer. And then we can optimize the following objective, which is the dual form of the previous optimization problem. And then in here, we just add the two together with a hyperparameter lambda in here. So we can decide the lambda empirically to based on the result of our generated adversary example. And then typically we can run the Adam optimizer within 100 iterations, and the generated adversary example are very good, which means that they can totally fool the model, and also the perturbation is very small. Also, recently, researchers are more interested in these so-called fast approaches. The benefit is that so these approaches don't need to do iterative algorithm. So they only need to compute the gradient once. So that is much faster than the iterative approach. So the basic idea is that, so we just want to compute the distance between x and x star directly based on the gradient, right? So we just compute this gradient, and then for the fast gradient sign, we take the sign of that. And for the fast gradient, that is what we develop. That is, we normalize this gradient and then add a b in front, and then add to the original distance. Yes?
How do you get the gradient with respect to x when it's a black box?
Right. So this is the so far I'm talking about how to attack the model in the white box model. Okay. So I haven't touched to the part of black box yet. So I will soon go there. Right. That's a good question. Okay. So these are right. So as I just explained, that these are all the different approaches to generate an adversary example in the white box model, and then the problem is that we have to need to know this model itself. So the real question is, how can we attack the model without knowing these hyperparameters, and we don't even need, know the function f here, right? So there is an intriguing property called transferability. So that was also identified by the 2014 paper. It says that the adversary examples generated for one model can transfer to the other. So what does it mean is that, for example, we consider these shoes, and then the ground truth is a running shoe, right? So this image is generated for the model of VGG16, which was a state-of-the-art model for ImageNet. And then based on for that model, we can misclassify this image into the military uniform. And then interestingly, when we generate this image, we only touch the model of VGG16. But when we evaluate over several other models, like the state-of-art Reson model or GoogleNet model, they are all classified into the wrong class, even though the classes are different, right? So this demonstrates the transferability really exists even in these state-of-the-art models. So then, based on this property, we can we can build the following attack scheme. So the idea is that we have the black box system. Then the adversary can generate a white box model themselves using different kind of technique. And then the adversary can generate adversary example against those white box models. And then with a high probability, this adversary example will transfer to that black box model. Yes?
So if the system that is, so if we can use these adversarial examples to retrain the underlying neural network,
yeah,
then won't it become robust to this kind of attack?
This is one of the most hot topic discussed in this area, and we are writing some papers to show that this is not indeed the case, right? So So there is a long debate whether adversarial training is helpful or not to defend against those adversary examples. But actually, we found that they are just another form of overfitting. That can so the retrained model just overfit to those generated adversary example. But you always have other ways to generate adversary example that can still fool the retrained model. Right. That's a good question. Yeah.
In this case, white box model is trained independently of the black box, or is this an assumption?
So there are different approaches. One approach is that you can generate this white box model using the so-called surrogate model. That means that you have a class of input, and then you submit them to the black box model, and then you can get the answer from that, and then you can train a model yourself using the white box model. then using this way, that's called the surrogate model approach. But in our experiment, we just train a white box model ourselves. For example, using the ImageNet dataset, we are not touching this black box system. For example, the clarify.comm at all. And then I will show very soon that they can still transfer, right? So, okay, so this is the basic scheme. But here, before I go into the detail, I want to make a distinguish between the two classes of attacks. One is called the non-targeted attack, and the other called the targeted. For example, for the ImageNet dataset, there will be 1,000 different classes. For every image, it has a ground truth. So we say that it's a non-targeted adversary example if the model will classify the image into any wrong class. Right. So you have 999 different choices for you to fool the model. But for the targeted adversary example, we manually pick a class that is far away from the ground truth. You will soon see how we pick the model, how we pick the target label. And then, so in here, over the 1,000 different classes, you only have one choice to fool the model into. Okay, we found that for the non-targeted adversary example, they transfer very well. So I just don't show their performance. But for the targeted adversary example, the transferability is very poor. So how to read this table? So we basically gathered 6 different kind of models from ResNet to Inception. When we did this, the latest Inception is still Inception v3, but right now they are v4. So we generate adversary example for different rows. So first of all, we collect 100 different images that can all be classified correctly by all these different models. And then we generate adversary example for different rows. And then we evaluate them over the different columns. And then for each cell that is based on this, that is the matching rate of how this generated adversary example perform. So what is the matching rate? That means, for example, for this cell, that means we generated the targeted adversary example for VGG16, and then we evaluate on ResNet 50, and we want to see how many of them will be classified into the target class that we manually choose. Right, and we found the accuracy is the matching rate is only 2%. That means only 2 out of 100 images are classified by ResNet 50 into our designed target class. But this is not because our adversary examples are generated poorly, because for the main diagonal, we can see that the accuracies are all 100%. That means they can all fool the model that you are using to generate the model. It's just the transferability is poor. So, okay, then here is the thing. So, for example, we have this water buffalo image, and then for clarify.comm, they also can classify that very well. And then how can we make clarify.comm believe that it's a rugby ball, right? So here we can see the concepts are very different from each other. Okay, as we mentioned that the transferability for generative for one model is very poor, so our idea is very simple. So we can ensemble all different kinds of models, and then we can generate the adversary example based on the ensemble model. Then in this way, we hope the transferability of this generated example are better. And then our experiment indeed showed the case. For example, for this, okay, I admit there are a lot of noises on here, but you should still be able to see this is a buffalo or some kind like that. But in the label return from clarify.comm, we can observe that pastime, ball, sport, and games, which are very relevant to the target label that we gave, which is the rugby ball, right? So then we say this is a successful target attack. And then I also like to show you something more. Like, for example, this is a broom image. And then we want the clarify.comm believe that it's a bird. And then by adding some noise, it indeed believes so. So it indeed believes the most likely label for this image is a bird.
Do you have a picture of the noise you add?
Unfortunately, no, right now. So, but we have the image in our repo, but not in the slides.
So in the noise image, can you recognize some bird or some?
No. So they just look like random noise. Yeah. Yes.
It seems like Clarify would be using one of these state-of-the-art image. It seems like Clarify would be using one of these state-of-the-art object recognition images, like Resident 152 or something. Right?
I'm not sure, but but clearly, right. One clear thing is that their label set is totally different than what we are using, like the ImageNet labels. So the ImageNet labels, like the Jacquemin, doesn't appear anything in here.
So are the image labels from ImageNet a subset of what they're showing? Do they have extra labels?
That might be possible, but so far the key point is that we don't have any knowledge about this.
I guess my point
Right,
was
so-
that underlying classifier is probably won't
Right, but
necessarily
so actually we talked to Clarify people during iClear, so where this paper is published. So and then they also didn't mention that they are not using. They are also not mentioning so what model they are using and whether this is because maybe the model is is indeed ResNet or it is because something like that.
Or it could
So.
be they're worried about IP issues that they're
Right.
using
Clearly
Microsoft
they don't.
Clarify.
Right. Clearly they don't tell us. Right. But these are just some results that that we can show. And also the last one is a fruit. It's kind of a fruit, and we want to make the system to believe that it's stupa, and actually when we generate this, it believes that it's a tempo, which is a synonym of the stupa. Right. So, okay. So. For this work, we demonstrate that it is not necessary. Oh, I also want to mention that for this we increase the scale of the perturbation so that the noise level is very large. But actually, when we decrease that to about a half, so we just don't have demonstration here. But when we decrease that, it can still full clarify, but just with fewer examples, fewer successful examples. Right. At this level of noise, we can, so out of 100 examples, there will be more than 20 examples that can fool the system successfully, right? So, right, this is just something that I like to mention. And then the main takeaway here is that to fool this kind of system, you don't even need to know the model deployed into your system, but you can still perform successful attacks against these kind of models. So this highlights the importance of why we need to study this. Adversary example because this will make the attack scheme very simple to deploy in the real case. Okay, so besides the yes.
So in your motivating example before with the traffic signs and so forth, there it's not the image that you'd have to change in some way in an adversarial way. It's the real world that you would need to change.
Yes.
So it's a human.
Yes, exactly. That's a very good question.
So whether or not you know the model. So can you do that?
We will see soon, right? Because we are also experimenting this. So, but there is a paper released from CMU. So they show that they design some paper glasses. So their target is a face recognition system, and then you wear the paper glasses, and then you go into the camera, which will identify whether you are some celebrity, and then they can make the system believe you that you are some celebrity like Barack Obama or someone like that with a very high confidence. So this demonstrates that it is indeed possible to do this real world attack. But so far for the traffic sign, we haven't done enough experiments yet. But I hope more results will be coming soon. Yes.
So what would be the practical? I mean, the practical scenario of attacking the system? Like you catch the image that somebody sent the sample, and then you.
Right. So we hope that, for example, like I demonstrated before, that in in the autonomous driving system, so they just use a camera to catch those different traffic signs. And then this is the simplest target attack scenario that you can apply this technique. For example, you want to kill some car, for example, just for example, and then maybe you can right.
It sounds like network security problem because you catch the image and you just give the another image instead of adversary.
Oh no. So like the question that I just answered before, the image is captured by the camera on your device. Right. So we don't need to we don't need to inject adversarial camera for you. So we just, for example, we can just plot something on the traffic sign or something that is almost invisible to human beings, but you can but for the camera which can capture that image sign, then it already automatically fool your system.
Can you really find the adversary example in the nature? I mean, you have to make.
So let me tell you one experiment done by Google. So this is done by Google. So they generate an adversary example, but this is not by nature. But they generate an adversary example and then print that on a paper, and then they use the camera to take a photo of the paper, and then they will recognize what this photo is about, and then in this way they can fool the image classifier within the phone entirely. So in this setting, all the devices that you are using, for example, the tool, the camera in the tool, the phone, the camera in the phone, are all your device. So we are not right. The attacker doesn't plug in any kind of adversarial tool into those devices, but only the image itself is injected some adversarial perturbation. Right. So I hope this can answer your question. Okay, I think right. So we need to move a little faster for the following part. So we also demonstrate that generative models are also vulnerable to these kind of adversary examples. So can I ask how many people here are familiar with generative model? Okay, pretty a lot. So then I can save a lot of time. So basically, a generative model contains an encoder and a decoder. So the encoder part will convert the original input into a much shorter vector representation, and the decoder will decode the shorter representation, which we call embedding, into the original vector. So we hope that so the point of generative model is that the decoded image will look very similar to the original image. But we demonstrate that we can inject noise onto the original image so that the decoded image can be totally fooled. So here is an example. This is the MNIST. So this is the original image. If we train a very good variational autoencoder, and then the recovered image look very similar to the original image, right? And then in this case, we set the target image, say 0. And then we can construct the so-called adversary examples that just look like printing these digits on a bad quality paper. So there are a lot of background noises here. But the point is that, very amazingly, after the reconstruction, everything becomes 0. Right. So this demonstrates that this generative model is also very easy to fool. And it's not only for digits, but also for, okay, this is also the digits, but the digits on the real street view, they can all be reconstructed into 0. And even faces can be reconstructed into a woman's face. Okay, so by here we demonstrate that all these kind of VAE like generative model are still vulnerable to adversary examples. Okay, then you may be asking questions about GAN, but we don't have an experiment here, but our suspect is that GAN is also likely to be vulnerable. Okay, the next one is that we also test whether this kind of deep policy, for example, the reinforcement learning system, are also vulnerable to these adversary examples. So we studied this A3T, which is a combination of actor and critique parts into the reinforcement learning system. So I want to check how many of you are familiar with this A3C algorithm already. Okay, so maybe a half of you. So I will do a brief introduction. So for the actor, so A3C is a combination of actor and critiques. For the actor part, it is basically a policy network. For example, when you are playing this Pong game, then based on the input image, the policy network, the actor part, will decide whether you go up or go down. So the decision is totally based on the current state itself. Then for the critique part, it will compute a value function to evaluate if you take some action, then how much reward you will get in the future in the long run, right? So one is instant. So the actor part is only based on the current frame, and the critique part will consider the reward in the future. So if you understand, right? If you don't understand, then you can just take it. Okay. So we demonstrate that we can train a A3C network that can play very well, which is the left hand side. We can see that it can easily win the baseline approach, but actually we can inject the adversary examples into every frame, and then to fool the policy network, and then basically we can observe that basically the same agent used by the left hand side and the right hand side, but on the right hand side it cannot catch even a single ball. And the more interestingly, I believe you cannot observe the difference between the left-hand side and the right-hand side. But I can tell you that on the right-hand side, there are already adversarial perturbation injected, right? So this demonstrates that attacking the policy network, it is very effective to attack the system. But more interestingly, you don't even need to attack the actor part. You can attack the critique part, which is the value function. Then when you attack the value function, it is one interesting observation we found is that you don't even need to inject every single frame. You only need to inject the adversarial perturbation every 10 frames. So this will reduce a lot of the adversary example that you need to inject it, and which also means that you can weaken the threat model that you have. Yes.
Are you training in the presence of the adversarial
No.
examples? So
They are all trained with the original model. Right. So we have experiment that adversary retraining is indeed helpful in this case, but I just don't have the results showing in my slides. Yes.
Is the value function used during training rather than inference? Or?
Yeah.
So
of course, yeah.
Why would attacking a value function during inference have any effect on the policy that it's already learning?
Right. That's a good question. Unfortunately, I cannot answer this question right now, but I can double check. Right. Yes.
Oh, yeah. What do you mean by attacking the value function?
Pardon?
What do you mean by attacking the value function?
So as I mentioned, that there is a actor part and there is a critique part. So basically, the last experiment only attacked the actor part. So this experiment attacked the critique part of the model.
Okay.
Right. So. Okay. So by demonstrating this, so we are not. So this Pong game is just a simple example that we want to demonstrate. But more importantly, we want to demonstrate that this kind of reinforcement learning system, which are heavily used in, for example, robotics and self-driving systems, are also very vulnerable to these adversary examples. And also, to attack these systems, we don't even need to inject adversary examples into every frame, but we can inject them sparsely into, for example, every 10 frame or even every 20 frames, right? So, okay, so that is the first part about our study on adversary examples, and then in the following I will discuss. So this shows that using this end-to-end neural network is vulnerable, very likely to be vulnerable to these so-called adversary examples. Then an alternative is that we return back to these discrete programs, or hybrid programs which combining the neural part and the discrete part, then the second part of my talk will be introducing some of our work about how to use deep learning to improve the security of these kind of programs. Yes.
So for the first part of the talk, what is the overall message that you have now? That is the situation hopeless, because you said that even if we train these networks with these adversarial examples.
That's a good question. Yes. So the first message that we want to send is that these adversary examples need more attention from the research community because they are so prevalent in all different kind of systems. So here are just some demo examples that we demonstrate that adversary examples exist. But for a lot of other systems, they also exist. So and also it also highlights the importance of we need to build the defense, and by showing that we can employ a very weak threat model, we demonstrate that why building a defense is a very challenging problem. Because we almost demonstrate that you don't even need to know the model, the white box of the model, then you can attack the system in the black box setting. So then it also shed new light into how should we consider the defense algorithms in future research. For example, when we build the defense, whether we test that in the white box model or whether we should test that in the black box model, right? So yeah, so I think these are the main takeaways of these works. Yes.
Is there an assumption that's the white box model, the model that you're using to generate the adversarial examples is kind of similar to the black box model that you don't get to see, right? You could imagine that Clarify had invented ResNet and not told anyone about it, right? And the rest of us were stuck using DTG or AlexNet or whatever. And you could do an ensemble over those and generate adversarial examples.
Sure.
But then, I mean, would you still be able to generate adversarial examples for that?
That's a very good question, and that's the most important open questions in this field. So actually, we did want to study the similarity between different models. At least if we just look at the model superficially, their model architectures are totally different. So they share the parameters trained, even for the same model, that we train with two different sets of random initialization, the parameters in the model are also totally different, right? So superficially they are not the same, but there are some common similarity in between of them. For example, they must all have a very good test accuracy. That means when giving normal original image, the prediction accuracy should be similar. Right. This is right. If we look at them at the one high level, this is the only similarity that we can talk about right now. So and then there are a lot of theoretical study. So we have some theoretical results in our group that we are writing, and right. Actually, Stanford also have some theoretical results on some simpler network that we right. We want to show that if the model's test accuracy are similar, then whether the decision boundary should have some similarity in between, right? Which is the main purpose. The main purpose of adversary example is that you can generate adversary perturbation so that you can go across the decision boundary, right? So the decision boundary, that is the most interesting thing we are studying. But so far we don't have a very clear understanding of that yet, right? Yes.
Thank you for a great talk. I'm wondering what if we apply a bilateral filter or some denoising algorithm before the main CNN application?
Yeah, that is also considered by existing work, and then right, people usually show that they can also be fooled, right? So this is the high-level message that so far almost all the existing technique can be attacked, right? This is the one sentence high-level message, but we are not giving up. This is another important message here. We are still trying to find whether we can build an adversarial resilient system. Okay, so shall I move to the next part? Okay, yeah, thank you. So for the second part, so basically I will showcase some of our study to show that we can employ deep neural network to achieve much better performance on binary analysis, which I will talk about right after this slide. We also demonstrate some of our program synthesis work on different kind of input types. Okay, so let's just start with the program analysis. So one of the hottest thing in today's world is so-called Internet of Things or IoT devices, right? So there is a prediction that by 2020 there will be over 50 billion IoT devices in the world, right? For all these different devices, then there is an important issue is their firmwares. So you can consider the firmwares of the IoT devices as some kind of operating system built to drive the device to work. And then, there are some properties of these devices. One is that these firmwares are written, their instruction set architecture is different. For example, some of them are x86 structures, and many of them are ARMs and MIPS because they have lower power consumption, right? So and also to implement these firmwares, the binary code are also in different format, right? So is that clear what binary code means? That basically means the executable code that can directly run onto the CPU, because it always gets confused when we jump into this part from the images, right? So I hope this is clear. And then there's a very severe problem is that when we build these firmware images, so the current practice is to employ some common open source code. For example, one of the most heavily employed code is the OpenSSL, because every single IoT device requires a secure connection component. And then OpenSSL just fits this goal. And then, so this means that once one vulnerability identified in this source code, that will affect the millions or even billions of these IoT devices. The most important, significant example is this called Heartbleed. That is, so I think many of you should be familiar with that. And then a lot of systems in the world have been affected by this vulnerability. So when these new vulnerabilities are identified, so our problem definition is that we hope to design a mechanism so that when these vulnerabilities are newly detected, then we can have a very fast mechanism to see which firmware images in binary code are affected, and how can we fix them, right? So let's give it a more precise definition. So we are given two programs. One is the vulnerability that may be compiled from the source code. For example, the pre-patched source code. And then the other is just a binary code. We don't know which architecture it is, but the code itself can tell us which architecture it is. And then our problem is want to detect whether two programs are similar. So this problem is very challenging given this context of IoT devices, because the architecture are so different, so that even the compiled code may have very various of forms. For example, their control flow graph may even not be the same. Okay. And so the ISAs are different. Also, the compiler used to build this binary code are different. Also, the compilation options, for example, whether you are using O1 optimization or O3 optimization, they are also different. So there are so many various, so that if you just consider using a hash-based approach, for example, you can compute the SHA-1 signature of a binary code, and you want to match whether the SHA-1 signature matches the vulnerability. So such kind of work doesn't work. Idea just doesn't work, right? So then how can we solve this problem? So in the research community, so basically we consider this of architecture to solve the problem. So we have a firmware file, so we have the vulnerability. Then we can use a disassembler to extract the code graph from the original binary code. So at least in this code graph, we have some structure. That is basically a graph with some attribute on each node. And then we compute an embedding of this code graph so that they will be converted into the vector space. And then to test whether two codes are similar or not, we simply use the cosine similarity between the two embeddings. Right, this is the high-level idea. And then, so as you can see, the most challenging part is how to define this embedding algorithm. Right, the existing work employing this idea use bipartite graph matching algorithm to compute the embedding. For example, the state-of-the-art result that demonstrates better performance than all previous approach was just published in CCS 2016, which is our baseline in our comparison in the following, right? So, and we found this bipartite graph matching-based algorithm is first of all, it's very slow because bipartite graph matching is just slow. And also the effectiveness is not that good because this is a deterministic graph, doesn't consider anything else. Okay, so then our approach takes another idea that we can use a deep neural network to learn this embedding automatically. Right, and then in this way, then we can avoid the expensive bipartite graph matching, and so that to compute the embedding vector, it can be very efficient. Also, we can train the network effectively so that the embedding contains much more semantic information than this manually designed ad hoc approach. Okay, so I won't go into the detail of how we build the network. Basically, we borrow one from this paper that is called structure to vec. So basically, for a code graph, this structure to vec can convert the input into the embedding. And then the real problem is how do we train this network? Because the original paper requires a label for each input so that they can be trained. But in our setting, we don't have a label, right? So to mitigate this problem, we just use a CMUs network. For example, the CMUs network just contains two identical networks inside it, and then compute the cosine, and then you only need to give two graphs and the label whether they are similar or not, right? So, and then in this way, we can use to combine the structure to vec work and the CMUs network to train the network. And then I'll just give you a few statistics about how our system works. So first of all, the most important metric that we are caring about is the serving time. So in previous work is the CCS 16 paper that was just several months ago, and then for every single input file, it will take a few seconds to a few minutes to generate the embedding for just one input, right? And using a deep neural network, it just takes a few milliseconds. So if we compute the improvement, that's from at least 2,500 times speed up, and to the best case, we can achieve over 16,000 times speed up. So this is a huge improvement in terms of the serving time. And also the training time is also much reduced. For example, in their original work, they require a clustering algorithm in the training, which needs to compute a pairwise component of a very giant matrix. So the training time takes more than 1 week. And in our case, to train one good model, we only need less than 30 minutes. So that is very fast to train. And also for the effectiveness, so this is just a table that we demonstrate the correct vulnerability that we found. So for example, we have a large data set of over 400 million samples of binary code, and then we get the most. So this is just one vulnerability, but we have several vulnerabilities. in our experiment. So we get the most likely, the most similar ones in the data set. And we manually look into them whether the vulnerability exists or not in this data set. So we found that among the top 50 results, we can confirm that 42 of them are correct, are indeed vulnerabilities. And in previous work, the number is only 10. So this means that we on average, so this is the best example, the best vulnerability that we can have. But on average, within the top 50 results, we can identify 25 more vulnerable files in the top 50 results. That's already 50% of accuracy improvement. Okay, so any questions so far? Yes?
Just to clarify, you mentioned you don't have training labels, but how are you training the CMUs network?
Right, that's a very good question. So we have the source code, right? For example, we can take the OpenSSL source code, and then we can compile that into different architectures and using different compilers and using different optimization levels. And then we can get a set of different binary code. And then for the same function, in different ISA, if they correspond to the same source code, then we label them as identical. Or otherwise, we label them as different. Right, in this way, we can somehow get the ground truth so that this network is trainable. Right, okay. So any other questions? Yes?
So how will, so what would be the input structure, the graph, and then what would be the basic architecture to take the input graph?
Oh, the input is just a graph, and on each node there will be a vector. There will be a small short vector that is manually extracted using some heuristic approach. And then so basically the network is kind of similar to a belief propagation that will propagate the vector on each node onto the adjacent node.
So it's
Because
matrix, it's going to be matrix that represent the two nodes are connected is going to be one.
Yeah. I will take that into consideration. Right. So all the edges in the graph are directed. So the information just propagates through that direction from the source node to the target node. This kind of thing. So I don't go into detail of that because that is maybe not the most important part. So the main takeaway message of this work is that we just want to demonstrate that using deep neural network, it can help solving these program analysis problems, and then it can be more effective and more efficient. So and also the program analysis can be a novel application domain of this of deep learning technologies. Okay. Yes.
Just a small question. Thank you for the great talk. Do you think it's possible to also detect new vulnerabilities? So I could imagine that you discover a higher level structure,
sure.
Which could correspond to a whole class of vulnerabilities. So do you think that
that's a good question. So this is just a starting work to demonstrate that deep learning can be used, but that can be a next step that in our consideration. Right. But so far we only did this work, and then we are still continuing to some other binary analysis tasks. Right.
So you said that you actually given the vulnerable source code you compile the different options, different platforms, right?
Sure.
What if you taking all the binaries for different options, different platform, and just have a hash function?
Yeah, that's what I mentioned at the beginning. So because there are too many of them, so you cannot exhaustively enumerate all.
Try one by one.
Right. The question is you can.
You have dozen of hash functions.
So it is questionable because in our consideration we only found about around 12 different kind of SHA-1 signatures in our so that can be constructed using our compiler. For example, just GCC with different compilation option. But in the dataset, we found over 20 different kind of SHA-1 signatures. So we don't know, and they also doesn't match the signature that we have that we generated automatically. So this is why I mentioned at the beginning of the talk, this kind of hash function-based approach is not will not work well because there are so many variants, you cannot do a exhaustive search. Mm-hmm. Yeah, that's a good question. Okay, I think I need to move to the next because I still have a lot of things to talk about, but we don't have a lot of time. So right, so in the following, I will talk about our work on program synthesis, and this is a simple work that was originally published from Microsoft here. So the task is that given a natural language description, we want to predict a so-called if-then program. So a if-then program is basically contain only two parts. That's very simple. So if, which is called trigger, and the then action, right? Only two parts. So this is the simplest of program that you can have, right? So what you can do? So we observe that there is a strong correlation between the terms in the sentence into the prediction that you need to make. So this means, for example, when we have these post photos in your Dropbox folder into Instagram, then the keyword Dropbox will hint that the trigger is very likely related to Dropbox functions, and the Instagram there is hints that the action is very related to Instagram. So the basic idea is that you can use attention to put different weights onto different tokens, so that you know where is the most important part in the sentence when you make the prediction. However, using attention itself may make mistakes. For example, you may consider the Dropbox is related to the action and the Instagram may related to the trigger, then the whole prediction is wrong, right? So we found a lot of examples of this scenario in the validation set. So this approach is not good. So this is why we introduced this called latent attention mechanism that can help to make this prediction. That is, so in the sentence, we found there are some, like either proposition or some other words that help you to locate where is the trigger and where is the action. For example, this word to indicate that the first part of the sentence is more related to the trigger, and the second part of the sentence is more related to the action. So in this way, we can build a so-called latent attention architecture, which will put attention first on where is the keyword, and then based on this keyword, we decide how to put attention on when we predict trigger and actions. And then we observe that our approach can achieve the state-of-the-art performance on this different kind of task where in the left-hand side we only predict the channel, but on the right-hand side we only predict the channel and function. So I may not have enough time to talk more about this. So if you have questions, I'm very happy to talk about that after this. So the main takeaway of this work is that the natural language is a very convenient way to represent the functionality of the code to be synthesized, but it is very hard to guarantee that they are all correct. For example, as we can see, that accuracy is only 90%, so it is not 100%. And also, we are not synthesizing the argument to each function, right? So, and this is the latest part that most of you may be interested. That is, we want to try to see whether we can do input-output pair program synthesis, or you can also call that PBE, program by example. So here, the program that we want to synthesize is a parser. For example, we have an input example. We have an input, which is a token sequence, and we have the output tree, but we have nothing else. So we want to infer. So we also of course don't have the grammar, the production rule of that, but we know that they all belong to the context-free grammar. So we want to learn this parser based only on these input-output examples without any other supervision. So this problem is pretty challenging when the grammar is unknown because of the following issue. So first of all, for these tokens, the input tokens and the non-terminals in the tree, there should be a correspondence that needs to be learned. And second, you need to know the order of the input tokens may not directly correspond to the previsit order of the prediction tree. For example, this is a program written in CoffeeScript, and then in the parse tree, the later part of the program comes first in the parse tree. Okay, and also we need to learn this association. For example, in this part, if we want to build one if x as a subtree, this is not valid because the association doesn't work like that. So all these challenges make this problem very interesting to be considered. And so here I briefly review some related work in this field. The first one that will come into our mind is a sequence-to-sequence-like architecture. So, and we will demonstrate, so this is indeed our baseline approach to compare with. And we will demonstrate that this kind of approach is hardly generalized to longer inputs. Also, there are a lot of work coming from Microsoft here. For example, the R3N by Danny and Robust Field. They consider to construct huge network that will take the examples as the input and then predict the program as the output, right? So this is the basic idea. But one problem is that the program's length is very limited. So I wouldn't say that is a limitation, but I think our work is considering a more complex class of programs that having the different design goal between these lines of work and our research problem. And there's another important class of approaches that is called NPI, or Neural Programmer Interpreter, that basically learns a neural representation of the program. What do I mean is that there is an underlying environment. For example, you can consider the stack or the machine or the RAM. They all belong to the environment, which can provide observations. And then there is an LSTM that will take this observation as the input and then predict what is the next function to be executed, or the next primitive to be executed, right? And then, so this NPI has demonstrated huge success on simple algorithms like topological sorting or quicksort. But to train these NPIs, you need full supervision on the execution trees. So you need to know every single step which instruction to be executed. So, and also the programs implemented to be handled by NPI is, right, that is moderately complex, but not too complex. For example, the quicksort example studied in previous paper, which is the most complex example, can be implemented in Python in 3 lines of code. But in our example, our parser needs at least tens, one of the examples require more than 100 lines of code to implement the full parser. I'm not even counting the other auxiliary functions to make the implementation simpler. Okay, so here we describe the design goal. So first of all, our supervision contains only input and output pairs. And second of all, we hope to achieve full generalization. That means once the model is trained on a small data set, and it should achieve 100% accuracy on arbitrarily long test data. It should also be generic. So we hope that our model, our approach can be handle different styles of languages without any specific tuning, right? Not with specific tuning, so without any additional design to tailor for the different languages. And then we will demonstrate in our example that our approach can handle both imperative while language and the functional lambda language. And right, so this is the high-level idea of our approach. So we want to learn a neural program operating a non-differentiable machine. So then here is the idea. So given an input, so the neural program will constantly emit the next instruction to be executed by the underlying parsing machine. And then the parsing machine will return like the environment observation or argument to the neural parsing program so that it can predict the next instruction. And then after several iterations, then the neural program will emit the final instruction. That means the program has been executed and the execution can be terminated. And then in the end, the prediction, the output should be emitted by the parsing machine directly. So why we are interested in this? Because we found several other architectures, several other problems share the same can be modeled in the same module. For example, in the theorem proving, we have a premises and we have a conclusion. We want to construct the intermediate lemmas one after another. And then for the problem synthesis, the general problem synthesis, we can have the precondition and the postcondition. And then we can generate every line of the code to meet this requirement. And more interestingly, architecture search also belongs to this category. So we have the input data and we have the output prediction. We want to generate the intermediate representation of different of the internal structure of the neural networks, so that they can so that the output can be very close to the ground truth. Okay, so. And then by employing this idea, we need to do two levels of innovation. One is we need to define a new non-differentiable machine first, and also we need to design a new neural program so that it can be learned from input-output pair only. Okay. So to achieve this goal, we designed this so-called LL machine. So the name is called LL, but actually it's a hybrid between the LL parsing algorithm and the LR parsing algorithm. Okay, so I won't talk detail about this parsing algorithm, but basically it employs a stack structure so that it will parse every sub-expression in a new stack frame. And once the sub-expression is reduced into a single into a non-terminal node, it will be returned to the previous stack frame so that it can be further executed recursively to construct the entire large tree. Okay, so this is the basic idea of the LL machine. And then for the neural parsing program, one property of the stack machine is that on every frame of the stack, so it not only contains one element, but contains this so-called FID and the list of different non-terminals that will be constructed as the children of the root. Okay, and then for each, so the LL machine will contain 5 different types of instructions, and then 2 of them, one is called reducer, the other is called call, and then 2 of them will have arguments. So our neural parsing program will base only on the stack top. This is why this algorithm can be generalized to arbitrary input, because it's not depending on the whole input, but only on the stack top. And then based on the stack top, it will predict the instruction. One LSTM is used to predict the instruction time, and 2 other LSTM are used to predict the arguments. So, right. So if you are interested, I can talk more about the architecture after this one. So by employing this kind of structure, we can guarantee that it can fully generalize to arbitrary input once we design the training corpus. Okay, so the main challenge is still here. We have only input-output pairs, so we don't have the execution traces. Then to recover these execution traces is a very challenging problem, because even for a very simple input, x plus y, it has 9 steps to convert the input token sequence into the final output tree. Right. So then our idea is to use a reinforcement learning based algorithm. But if we just employ for example, the policy gradient algorithm naively, then we have a lot of trouble. Right. So here I will briefly mention the challenges that we will get during this process, and then briefly explain our solution. So the first one is that the policy gradient will be simple, will very easily get tracked at some local optimal. So what I mean is that So for every input, because it is, if you only look at one input, then there are various kind of a set of production rules that can convert the input into the parsing tree. And then in this case, so the policy, if we just look at one example, then the policy network can get stuck into any of these grammar or production rules. And then also, if we only look at one of them, it is unclear which one is the correct one. Right. So this is the first problem. And also, if we combine several examples together, it is very hard to train one policy network to feed them all. So, for example, to achieve 100% training accuracy. So during our training, if we just run simple policy gradient, we never observe that we can achieve 100% training accuracy on the training on any training data. Right. So then how we solve this? So the approach that we take is that the high-level idea is that, okay, for every input-output example, we have a set of feasible traces. Then we just want to get a combination of these trees. For example, for every input-output pair, we want to get one trace. And then, for example, a collection of 6 different input-output pairs, we get 6 traces. And then we just want to find the correct one so that one policy can achieve 100% training accuracy on all this training data. Then the basic idea is very simple. So for every input-output pairs, we we first collect all these feasible traces, and then we sample one for each pair. Then we can enhance the data set. So originally the data set has only input-output pairs, but right now we have input-output trees triple. Okay, and then we can train a policy network to see whether it can achieve 100% training accuracy on them. So if this is the case, then we find a good policy. Or otherwise, then we repeat to step 2, and we resample these trees. And also we have some algorithm to adjust the sample distribution about how we sample them. But those details you can take a look at the paper. I will not talk about them. So using this approach, we can solve the. So using this approach, we can. It's not easy, but it is feasible that we can find the good policy. But there is one subtle problem in here. It's because there are too many feasible traces. So if we just look at the sequence of a sequence of 9 instructions, each instruction may have 5 types, and for each type, for 2 of these types, they may have tens of possible arguments. For example, the reduce and the call instruction may have many different possible arguments. So that's a huge amount of huge amount of possible traces. Then how do we solve this problem? Right. So if we just train them, then the total number of feasible traces will be exponentially many. So that are too many. So to mitigate this problem, we split the search of the instruction type and the argument separately. So then we invent this idea called two-phase learning. One problem is that for each input-output pair, we only sample the trees without argument, so with only instruction type, and then so this set becomes manageable. And then by removing the trees, then it's not a full supervised learning problem. So then we invent a new weakly supervised learning problem algorithm to solve to solve how do we find the correct argument. So then we decouple the 2 problems separately. So right, because I don't have a lot of time, so I cannot explain too many details. But I'd like to demonstrate our experiment results. So basically, we consider 2 languages. They are not full-fledged language, but they are very simple languages. And one is imperative and one is functional. And then we compare to 2 baseline. One is the sequence-to-sequence model. The other is sequence-to-tree model. And then we build 2 training sets. One is the curriculum learning, because reinforcement learning requires a training curriculum. And then this curriculum data set contains only 100 to 150 examples of length less than 10. But however, for these two sequence-to-sequence model, they cannot be trained on this such small data set. So we enhance the curriculum learning into the so-called standard training set. By randomly generate 10,000 different kind of inputs of length 10. Then for the test set, we randomly generate 3 different test sets of length to be 10, 100, and 1,000. So we can observe that for the test set of which contains the example of length 1,000, the length is 100 times longer than the input training samples. Here are the experiment results. We can observe that for our approach, no matter we train with the curriculum or with the large data set, of course they are the same, they can achieve 100% testing accuracy on all these different data sets. But very interestingly, for the sequence-to-sequence model and the sequence-to-tree model, even on this standard training set, they cannot achieve 100% accuracy. And when they are evaluated on the longer, so if we evaluate them on the longer data set, the accuracy all drop below 0, all drop to 0. But even on the test set, which have the same length as the training data, the accuracy is less than around 20%. So that is pretty low.
C2C baselines don't have external stack.
Which one?
Baselines don't have external.
No, it doesn't have. Yeah. Right. So, right, that is on the while language, and for the lambda, for the function language, it is a little simpler because we can observe the test accuracy right now is more than 86%. Right, but for the sequence-to-sequence model, the accuracy is still very low. Right. So this demonstrates that our approach is much more effective in terms of the generalization and handling different kinds of languages. Okay, so the main takeaway here is that I want to promote this kind of building neural program, the model to building neural programs on top of non-differentiable machines. And then using this kind of architecture, we can achieve much better generalization property than fully differentiable neural networks. Right. So, and then we found that during our study, even though I don't talk a lot about that, but the design of the non-differentiable machine, for example, the IL machine, is very critical to make this program to be learnable. Right. So, yes?
So, still a little confused about the motivation of this parser learning problem. Right? So, where in practice are you going to get lots of input-output examples from?
Yeah, right. So this is a good question. So for example, when you design a new DSL, a new domain-specific language, maybe in some small applications, then in this case, you may not need to write a formal parser using Lex or YAC or ANTIR, this kind of tool. You may only want to provide, okay, this is the input, and then its parse tree is like this. And then I will hope you can provide the part.
So how many examples do you think would be needed related to the size of the grammar, let's say? Because then the challenge is between you write the grammar yourself, or do you provide lots of examples?
Right, exactly. So for the example here, right, that's a very good question. For the example in our experiment, we take around 100 to 150 different examples in the training set. And the production rule is around 100 different kind of rules. Right. I don't recall the exact number, but right, there are around 100 different kind of production rules. But the point is that it is very tricky to get those production rules wrong. Right. So, but you can demonstrate by showing, okay, for this input, its parse tree should look like this and not look like that. Then this is a much more intuitive way for human being to generate than writing the rigorous production rule. Right. So, right, but that can be a good question. But, and also for this problem, it is not, right, even though we think this problem itself is important, but also this is a first step of another project that we are building on, right? Yeah. So basically, that's here is our conclusion. So we have talked a lot about how building secure applications is very challenging, and demanding. And then we have demonstrated that this end-to-end neural network are vulnerable to adversary examples. Also, we demonstrate some preliminary result how we can use deep learning technologies to help program analysis and program synthesis. Okay, yeah. So so that's all. Here are all our collaborators, and thank you very much for the talk. I'm not sure if I still have time to take some questions, maybe.
More questions? One question. So,
You go ahead, I'll go.
So for the neural parser, how big is the neural networks? How big?
Oh, it's very small. So we only use one level of CM with hidden
How many
state.
parameters?
I don't count the number of parameters.
Hundreds. Hundreds or thousands?
Maybe thousands, because the hidden units is 5. There are 50 different. The hidden states is a vector of 50. So, and then the transition table. I think so. There is at least a 50 by 50 matrix in there. So there must be a few thousand parameters.
Yeah, actually, quick question about the architecture for neural parsing program.
Sure.
The stack is also non-differentiable.
Sure.
Is that continuous?
The stack is non-differentiable. So this is the whole point, yeah. Because we found that if we use the differentiable stack, it is very hard to get 100% accuracy.
I see.
Right. Also, this is also demonstrated. So this idea to combine the neural program with a stack is not new. So it was invented in 1990s, and that was called push-down automata. And then even in 2015, there is a paper on this topic, but they demonstrate that even for very simple context-free language, the accuracy is not 100%. So this is why this kind of differentiable machine is not within our consideration at the first place, because we hope our first goal is to achieve 100% general test accuracy, right?
Okay, that's some speaking here.
Yeah, thank you very much for being here.